Hi students. Okay, in this video we are going to talk about refraction of light. Okay, refraction of light is actually the idea of bending of light. Okay, so how does this come about? Basically, we know that when we shine a ray of light into a glass block, the ray of light in the glass block doesn't continue to travel in the same straight line as what it is traveling in the air. And we observe that the light has bent. Okay, you can actually search for the videos or images of all these refraction of light. Okay, so how do we actually use physics to understand this bending of light? Okay, so let's go back to our ray diagrams to help us understand. Okay, like before, okay, there are a lot of common terms that we are using throughout this lesson itself, this video itself. Okay, so I will start off with what we already know. Okay, firstly, okay, let's talk about the air and glass. Okay, basically anything under this line is glass, anything above this line is air. So when light ray coming from the air hits the glass at this point, okay, this light ray, we are calling it the incident ray. As per reflection, this angle here, we call it the angle of incidence. Usually we'll denote it by I. Okay, and the normal to the surface is just a imaginary line that is 90 degrees to the surface itself. Now, when a light ray comes in from air and hits the glass, okay, we actually will observe the light ray bending. And how does it bend? Okay, it actually bends towards the normal. Okay, so this light ray that bends, there is bent, okay, we call it the refracted ray. Okay, so refracted just means the bending of light. Okay, down here, this angle is now called the angle of refraction. Okay, so notice that whenever we mention this angle of something, angle of refraction, angle of incidence, angle of reflection, okay, it's always the angle that is in between the normal and the ray itself that we are referring to. Okay, so here are some things that you might want to take note, okay, of the light ray itself. So basically all these are observations that can be done easily. Okay, so what are the how does the light ray actually bend? Okay, it generally follows these few rules. Okay, when the light ray, okay, I'm going to draw a simple table here, okay? Okay, when the light ray travels from a less dense to denser material, okay, the refracted ray actually bends towards the normal. Okay, so we are actually using the normal as a reference now. Okay, it's important to remember all this as you go along, okay, because it will help answer a lot of questions easily. Okay, so what do we mean by denser to less dense to denser medium? Okay, in this case, we are talking about the optical density, okay, of the medium itself, of the object itself. So let's go back to this first diagram that I've drawn. Okay, so in this case, air is actually less dense than glass. Okay, so this current situation that I'm mentioning in the table itself is actually an example, okay, of what is happening when light ray travels from air to glass. Okay, so Of course, there's also the other way around where the light ray actually travels in the opposite direction. Okay, and let's make a guess. Okay, are you good? Can you make a guess? To tell me. Okay, make a guess on what is going to happen to the refracted ray if the light ray is traveling from denser to less dense medium. Okay, for those who are quick, you soon realize that it's actually the opposite of what is happening over here. Okay, so when the light ray is traveling from denser, which means, let's say, from glass into the air, okay, so denser to less dense medium, okay, the refracted ray bends away from the normal. Okay, so these are two important key points that you will have to take notes as you proceed through the lesson itself. Okay, so hopefully this table helps to summarize what you need to know. Okay, but this is not the end. Okay, because we definitely need to be able to do more than just describe. Okay, in fact, since we talk about optical density, we have a way of describing the optical density of mediums with respect to each other. And this description is what we call the refractive index. Okay, think of refractive index as a form of numerical number that is comparing the densities, okay, optical densities of various mediums with each other. Okay, so there's an important formula for us. Okay, and this formula is n is equals to sine I over sine R. Okay, what is n, I, and R? Okay, down here we have to be a bit more careful. Okay, n is actually the refractive index. Okay, it does not have any units. I repeat again, it does not have any units. Okay, I and R here, okay, are actually the angles of incidence and angles of refraction. But we have to be very, very careful as to how we actually apply this formula, because it's in this case, I is actually the angle of incidence when it's in the less dense medium, and R is the angle of refraction in the more dense medium. A bit confusing. Let's simplify it for you. Okay, sometimes teachers will tell you that I is actually the angle in the less dense. Okay, R here is actually the angle in the more dense. Okay, so let's apply. Okay, let's apply it so that you know what I'm talking about here. Okay, I'm going to give you an example here. Okay, we have a situation where down here, glass and air at the bottom. Okay, and the light ray is actually traveling from the glass into the air. Okay, so I shall illustrate it this way. Okay, and these two angles, okay, this is now the angle of incidence. Okay, the angle of incidence here is okay, random number. Okay, maybe 30 degrees, and the angle of refraction here is actually let's say 80 degrees. Okay, so question would be calculate the refractive index. Of the glass. Okay, so if you look carefully here, okay, if you just look at the formula and look at what we have drawn here, many of you would be stumbled, okay, because it seems like it doesn't match anymore. Okay, so perhaps can I get you all to go and try this now and see whether you can get the same answer as what I'm going to get later on. Okay, for those who are ready, okay, let's carry on. Now, for this particular example, okay, we want to calculate the refractive index of glass. So it's still the same formula, n equals to sine I over sine R. Okay, but look at what I'm going to use, okay? What number I'm going to use. Sine I here, I'm actually going to write sine 80 degrees. While R here, I'm actually using 30 degrees. Why is that so? If you look at what my condition for the refractive index is, I is actually the angle in the less dense medium. Air and glass, between these two, air is actually the less dense medium. On the other hand, R, okay, is the angle in a more dense medium. In this case, glass is the more dense medium here. So by applying it correctly, okay, you should be able to get this formula out as sine 80 divided by sine 30 degrees. Okay, and based on the calculator, you should be able to get 1.97 as a 3SF answer. Okay, so be very careful of how things are being applied here, because there are some conventions that we need to follow so that we continue to keep the pace. Okay, now this is not the only formula we have, because sometimes we do not have the luxury of knowing the angles. Okay, instead we are sometimes able to measure the speed of the light in the medium. Okay, now the strange thing about light in denser medium is that it actually slows down. Okay, when light travels from a less dense to more dense medium, it actually slows down, and because of it slowing down, it actually bends towards the normal. Okay, so this formula here, n equals to sine over sine R, is actually called the Snell's law. Okay, in the proper term, okay, in the proper physics law, physics formulas, we call it the Snell's law. Okay, it's a simplified form that you are seeing here. Okay, now there is another form, okay, another formula, which is n equals to c over v. Okay, n here is the same. N is actually our refractive index. Okay, c here, okay, actually represents our speed of light in air or vacuum. Okay, usually the difference between these two are so small that we don't usually distinguish them, okay, for our level at this moment in time. Okay, we know that the speed of light in vacuum is 3.0 times 10 to the power 8 meters per second. Well, v here is actually the speed of light in the medium. Okay, so we have this second formula that can actually calculate the speed of light in the medium itself. Okay, how did this came about? It's actually through experiments, okay, that we actually achieved this formula as well. Okay, so let me give you an example of how we are going to apply this. Okay, a ray of light, incidence is shined onto a glass block, and refraction happens. find the speed of light in the glass block if the refractive index is 1.44. Okay, so a very quick example on how we actually apply this formula that we have here. Okay, so this is our second formula. So N equals to C over V. Okay, so let's apply it quickly. In this question itself, we are already given the refractive index as 1.44. So let's apply immediately. Substitute immediately. C is something that we already know. Okay, C is actually 3.0 times 10 to the power 8 meters per second, which leaves us with V. So knowing 2 out of the 3 components, okay, we can actually calculate the speed of light in the medium itself, which should be 3.0 times 10 to the power 8 divided by 1.44, and this would give us a value of okay, give me a second here. Okay, this will give us a value of about 2.08 times 10 to the power 8 meters per second. Yep. Okay, so you realize that if I compare it to the speed of light, it has actually slowed down. Okay, so with this in mind, okay, we now know that there are 2 formulas that we can play around. N equals to C over V, as well as the other one, which is N equals to sine I over sine R. Okay, so hopefully this will help you in your understanding of refraction, okay, for a start. Okay, but it's not the end, okay, because we have a very special situation coming up, and this special situation is an extension of this portion where the light actually is traveling from a denser medium to a less dense medium. Okay, so I'm going to break up the segment here. Okay, so down here I will have 2 special conditions here. Okay, the first condition would be light is traveling from a denser to less dense medium. Now, when such a thing is happening, okay, we know that the light ray, when it's traveling from a denser to less dense medium, the light ray is going to bend away from the normal, okay, like this. Yep. So let's extend a little bit more. What if I increase this angle? Okay, what if I increase this angle here, theta, okay, that is between the normal and the light ray, okay, and how does it actually affect this refracted angle? Okay, can you think about it for a few seconds? That's right. Okay, if I increase the angle between the normal and the incident ray in the glass itself, the angle that is reflected outside in the air will actually go closer and closer to the glass itself. So to put it crudely, okay, this is what is going to happen if I increase the angle in between the normal and the incident ray represented by a ruler. okay, my pen, which is actually the refracted ray, will get closer and closer to the surface of the glass. Okay, so when that happens, okay, there will come a point in time where the light ray, okay, there is supposedly traveling outside, will now be on the surface of the glass. Okay, and this special angle that caused this to happen, okay, that means I caused the angle of refraction in the air to be 90 degrees. Okay, when this special condition happens, this theta is now called the critical angle. Okay, critical angle, we also can denote it by C. So you have to be very careful of the C now. Okay, this alphabet C. Okay, and what happens if I increase it even further? Well, when you increase it even further, the light ray will actually get reflected into the medium itself. Okay, and this is what we call total internal reflection. This situation here, okay, total internal reflection occurs. Okay, so let's talk about it again. Okay, I repeat. Okay, we know that when the light ray is traveling from the glass to the air, the light ray that is exiting will bend away from the normal. As I increase the angle of incidence in the glass, the angle of refraction in the air will also increase. And there will come a point in time where at a specific angle called the critical angle in the glass, okay, the light ray will actually cause the refracted ray to travel on the surface or in between the boundary of the air and glass. Okay, this will also mean that the refracted angle is now 90 degrees. If I increase this angle even further, then total internal reflection will occur. Okay, this is a situation where the light ray doesn't exit into the less dense medium anymore. Now, make a guess what this portion is actually explaining. That's right. Okay, we're actually explaining this thing called total internal reflection. Now, when I say total internal reflection, notice I use the word reflection here and here. This would mean that these two angles are actually equal. Okay, and the laws of reflection applies here as well. Okay, so when is the situation where you can see this? Okay, I hope you all have actually went into the swimming pool before. And for those who have dived under the water before, sometimes when you look up back into the surface while you're in the water, you will not be able to see the people outside of the water. Instead, you get a reflection of the bottom of the swimming pool. Okay, so that's actually a example of total internal reflection. Okay, there are other examples out there as well. Okay, I will leave you to explore the real world and find out what are those examples. Okay, but for us, this is actually the first condition for total internal reflection to take place, which is light is traveling from a denser to a less dense medium. Okay, so after my three diagrams here, you realize there's a second condition involved. Okay, and what's the second condition involved? Okay, the second condition involved is actually this, talking about this angle. Remember the critical angle? Okay, so any light ray, incident ray that is that is traveling in the denser medium to a less dense medium, okay, any angle that is bigger than the critical angle will cause this total internal reflection to take place. So I'm going to write it down in words here. Angle of incidence is greater than the critical angle. Okay, so only when these two conditions are satisfied, then we will have total internal reflection. Okay, but that's not all about total. That's not all for total internal reflection. In fact, okay, we have a formula that will help us calculate this critical angle. But this formula actually came from before, okay, where we talk about Snell's law, n equals sine I over sine r. Okay, so what's the formula? Okay, I won't really call it a third different formula, but it's like this. Okay, n is equals to 1 over sine c, where c here actually represents the critical angle. Okay, for those who cannot remember a third formula, the other way to remember is thinking about this situation here, where the angle of refraction is actually 90 degrees. Okay, so let me so-called derive it for you. Okay, n equals to sine I over sine r. Okay, at critical angle, r is equals to c. At the same time, the I is equals to 90 degrees. So by applying these two, n would be equals to sine 90 over sine c, sorry, which would come out as n is equals to 1 over sine c. Okay, so knowing the critical angle is very important because it actually is able to tell us whether total internal reflection will take place or not. Okay, so at this juncture, okay, I will leave you to explore the questions, okay, inside your 10-year series, inside your workbook, on how we can actually apply this, okay, so that we can you can get the practice itself. Okay, so I hope that this video will help you understand refraction as a whole and total internal refraction. Okay, I'll see you in lesson. Thank you.